Vibration Analysis Introduction: Forcing, Combination, and Mixing Frequencies. Agenda for this time is to talk about forcing function, combinations of machine problems, mixing frequencies. When a machine vibrates, the cause must be determined. The cause of the vibration is often referred to as the forcing function. A number of possible problems, any combination of these problems, and an infinite degree of each problem can cause the machine to vibrate. The amplitude of each problem can be either overstated or understated depending on transfer function, resonance, damping, frequency addition, and frequency subtraction. Therefore, very low amplitudes can be very serious problems in some cases, and very high amplitudes can be relatively minor problems in other cases. Frequency measurement and analysis makes vibration analysis work. Each forcing function has its own frequency, as indicated in Figure 1. If the problem is present, the frequency is present. The frequency can manifest itself as a discrete frequency or as a sum and/or difference frequency. Resonance, damping, frequency addition, and frequency subtraction do not affect the frequencies caused by vibration. This fact explains why frequency analysis is accurate, while amplitude measuring and trending are not accurate when diagnosing problems in rotating machinery. Defects in rotating machinery are caused by normal wear, improper lubrication, overloading, improper installation, improper manufacturing, etc. Vibration analysis identifies the problems or problem areas. Management, engineers, and technicians must determine the cause of the problems and direct the necessary repairs or find the appropriate solutions to the problems. Vibration analysis of rotating machinery involves calculating the frequencies the machine can generate and measuring the frequencies the machine is generating. Then, relating the measured frequencies to the calculated frequencies and machine installation can identify the problem. If the forcing function is a hit or an impact, the hit or impact may not be measurable. However, the machine response to the impact can be measured. Problems in machinery induce vibration and result in wear, malfunction, and/or structural damage. Vibration Analysis Introduction: Combinations of machine problems, the amplitudes of various frequencies, and the frequencies in rotating machines can add and subtract. These frequencies mix, detect, amplitude modulate, and frequency modulate in much the same way as signals in electronic mixers, detectors, and modulators. An electronic amplifier performs in much the same way as resonance. An attenuator performs in much the same way as damping. The simplest form of amplitude addition and subtraction is imbalance. When a rotor becomes out of balance, one side is heavier than the other side. This imbalance condition, or heavy place, generates a signal at 1 times RPM, as shown by the solid line in Figure 2. Balancing the fan is accomplished by adding an equal amount of weight to the light place. This weight generates a 1 times RPM equal in amplitude and 180 degrees out of phase with the imbalance, as indicated by the broken line in Figure 3. Since we live in an imperfect world, the signals may not cancel completely. Therefore, a small amplitude of the resulting imbalance may be present as indicated in Figure 3. Vibration Analysis Introduction: Mixing Frequencies. When two frequencies are present in a machine and a cause and effect relationship is not present, the high frequency will be riding the low frequency and the fast Fourier transform, FFT, will yield spectral lines at frequency 1 and frequency 2. If there is a cause and effect relationship, and the two frequencies can mix together, the result is amplitude modulation. Without getting mathematical, amplitude modulation is a time-varying amplitude. Amplitude modulation is caused when the equipment has some form of nonlinearity. This nonlinearity permits the amplitude of the two signals to add together when the signals are in phase, or subtract when the signals are out of phase. With amplitude modulation, the carrier frequency will be the frequency with the highest amplitude. The envelope of the varying amplitude will be the difference between the two frequencies. And FFT of these signals can yield spectral lines at frequency 1 and frequency 1 plus and or minus frequency 2. For example, suppose gear mesh frequency is modulated by gear speed. Gear mesh frequency is 1200 Hz and gear speed is 20 Hz. And FFT of this signal would then yield spectral lines at 1200 Hz, 1200 plus 20 equals 1220 Hz, and or 1200 minus 20 equals 1180 Hz. Descriptions of these frequencies are: number 1, 1200 Hz is gear mesh frequency. Number 2, 1220 Hz is gear mesh frequency plus gear speed. This is a sum frequency. Number 3, 1180 Hz is gear mesh frequency minus gear speed. This is a difference frequency. Number 4, the difference between 1200 and 1220 Hz, or 1200 and 1180 Hz, is 20 Hz, and this is also a difference frequency. Number 5, the source of excitation, or the problem shaft or gear, is usually expressed as a difference frequency. If the amplitude modulated signal is clipped or truncated, the FFT can yield an array of sum and difference frequencies of the two frequencies, including frequency 1 plus frequency 2. There are many forms of sum and difference frequencies. These frequencies will be discussed later. Thank you.